This is the lecture on fuel systems. Interestingly enough, maybe more important than how fuel systems work, which, don't get me wrong, I think it's important, is that how people operate it poorly gets them into trouble more often than the fuel systems themselves failing. Aviation gasoline. The purpose of having aviation gasoline on board the aircraft is so you can get a lot of energy for the amount of weight. There are other fuels that you can use, like hydrogen, but for the amount of energy you get out of the weight of it, it doesn't work out so well. The ratio of weight to energy is not as good as you'd like, and of course in aviation, carrying around a bunch of weight is a big issue. How does it do it? What is the function? By releasing the chemical energy in the gasoline into heat energy, and then of course that heat energy is what causes the gases in our cylinder to expand and push down on the piston and get energy to the crankshaft and then to the propeller. Aviation gasoline comes from crude oil or petroleum, black gold, Texas tea, that stuff that comes out of the ground. Same place you get kerosene and jet fuel, diesel fuel, car gasoline. That all comes from crude oil. And aviation gasoline, just like car gasoline and diesel and jet fuel, is made mostly of hydrocarbons. That is, molecules that have hydrogen and carbon in them, which is one reason why when you burn it you get a lot of carbon dioxide and a lot of carbon monoxide. Unlike car gas, which is now unleaded, it has tetraethyl lead, or TEL, and that is there to increase the octane. You can increase the octane other ways by refining the fuel or cracking it more at the refinery, but that costs more than it does to put the lead in. And lead does do some cooling, which is helpful. And then so lead does two things. The lead increases the octane, and it helps cool the engine parts, in particular the exhaust valve. And the bromides and chlorides are in there so that after the combustion process has occurred, all of the products of the combustion will leave the engine with the exhaust. Another term for that is called scavenge. It makes sure that all of the exhaust products are scavenged from the cylinder when the exhaust valve opens and the post combustion products are leaving the cylinder. You want all of it to leave. You don't want any buildup inside of the engine. Volatility is how easy something evaporates. The higher the volatility, the easier that it evaporates at a particular temperature. The lower volatility, the harder it is to evaporate. One of the problems with car gas being used in airplanes is that it has a higher volatility, and that means that it will tend to evaporate and go from a liquid to a vapor without getting as hot. So that's one reason it took a long time before you could get an STC, a supplemental type certificate, to use car gasoline in airplane engines, because they were worried that the higher volatility would mean that inside of the engine compartment, if the fuel line went past something that was really hot, the fuel might evaporate, turn into a gas or a vapor, and the fuel system isn't designed to run on vapor. The fuel pumps don't pump vapor, they only pump liquid. So you might have what's called vapor lock, and you can get that in your car. It tends to not happen anymore because the fuel is kept under higher pressures. But vapor lock is where the fuel turns into a gas, into a vapor inside of a fuel line, and it won't pump, hence the word lock. Low volatility is when it's harder to evaporate under a certain set of circumstances, pressure and temperature, but you need it high enough. If it's too low a volatility, then the fuel won't evaporate and it won't catch on fire. You need to understand that gasoline does not burn in a liquid form. It has to evaporate or turn from a liquid into a vapor, liquid into a gas, before it can combine with oxygen. So you need a low enough volatility that you won't have vapor lock, but you need a high enough volatility that it will evaporate and then catch on fire. Because if it's a really cold day and the fuel doesn't evaporate easily, then you spark plug can fire all day long, but if not enough fuel is evaporating, then it won't catch on fire inside of the cylinder. Of course, we've all heard about carburetor icing if you've had ground school in any way, shape, or form. And there's typically two reasons why ice forms in a carburetor. Here is a diagram, which we'll see if I can draw on it. Here we go. And here is the air. Here's the air. Let's see if I can get this a little thicker here. Oh, there we go. Air comes in this direction, and this right here is to the cylinders. Or to the engine, if you prefer. And here's our venturi. We all have heard about venturis in carburetors. Of course, Bernoulli's theorem says that the energy is the same anywhere in a closed system. So if we run air, I guess I could try blue here. If we run air through this venturi, and the velocity right here goes up, then the pressure is going to go down. So the static pressure goes down while the dynamic pressure or the velocity goes up. Now this works out great because of the lower pressure. This fuel in here gets sucked up out this little nozzle. So that's how we get fuel to get pulled into the air. And of course, the faster the air, the lower the pressure. The lower the pressure, the more fuel gets sucked in. Okay, this works out really good. However, with this lower pressure, that means that water, or the water vapor, this air, has water vapor in it, H2O vapor in a gaseous form. That means that it's easier for this water to freeze. For instance, at sea level, the freezing point of water is 100 degrees Celsius, which is 212 degrees Fahrenheit. But at 64,000 feet, the freezing point of water is at 37 degrees Celsius, which is 98.6 degrees Fahrenheit. So the higher you go, which is lower pressure. So as we climb, the pressure gets less. That means that it's easier to, the boiling point of water goes down, and so does the freezing point of water. So if we have a lower pressure, any of the water vapor that's in this air, it's easier for it to freeze. Now that's one of the two reasons why you can get carburetor icing. The other reason is this fuel coming out into the air. The first thing it's going to do is start to evaporate. Well, latent heat of evaporation, that is for this fuel to go from a liquid to a vapor, it needs heat energy. So it's actually going to pull heat energy out of the air molecules that are in here. And so the temperature of the air goes down, so the fuel can change its state of matter from a liquid to a vapor. And just at that moment when it goes from a liquid to a vapor, it takes all of its heat energy to change its state of matter, and its temperature does not go up. So it doesn't increase, the temperature of the fuel doesn't increase, it just goes from a liquid to a vapor, but the temperature of the air does go down because we're taking energy out of it. So the second reason why you get carburetor icing, or could get carburetor icing, is when the fuel evaporates and goes from a liquid to a vapor, it pulls heat energy out of this air, and of course this air also has water vapor in it. So if there's water vapor in it, oh wait, lower pressure, heat energy taken out to go into the fuel. That's why you can get carburetor icing even when it's higher temperature outside, significantly higher than the freezing temperature of water. Now, if you have fuel injection, the fuel injection systems on piston-powered airplanes, they squirt the fuel right into the engine just before the intake valve. So for instance, if here is a cylinder on the side of an airplane, and here's the piston inside, and it gets hooked up to the crankshaft, there is a valve right here. And this valve opens and closes, and just before this valve, right here, is where we have the fuel injected. And so there's no venturi, and we're so close to the engine, the fuel evaporating right here. The engine itself is hot. We don't have to worry about any fuel, about any carburetor icing. The diameter of this intake duct stays the same. We don't have a venturi, so you don't have to worry about carburetor icing since there's no carburetor, since there's no venturi, and this fuel changing from a liquid to a vapor is occurring right next to this really hot engine. So you don't have to worry about carburetor icing with fuel injections. Now, in both cases, whether it's a fuel injected engine or whether it's a carbureted engine, it's possible that the filter before the carburetor, before the fuel injection system, could get clogged up because of ice. So if that occurs, and you pull out, on a carbureted engine, you pull out carburetor heat, not only do you get the hot air coming through an exhaust shroud, that the air gets heated up by the exhaust pipes, but you also pull air in from a different place than the filter. It's now unfiltered, which is one reason why you don't want to run it a lot on the ground, because you're going to pull in air with rocks and dirt in it. But that way, if the carburetor if the filter gets clogged, you'll be getting air from a different spot. When you have fuel injection systems, like some of our newer 172s have fuel injection, it's alternate air, and it doesn't heat it up, but it does allow air in from somewhere else that's not through the filter, so that in case the filter gets clogged with ice, you'll still be able to get air to the carburetor. Of course, you've heard all this before, right? Detonation. Detonation is also known as, aka, knocking or pinging. If you've been in a car and you've tromped on the throttle, you pushed it down a lot, and you heard all that noise, that was pinging. If you've been behind a big diesel pickup truck and you can hear it knocking really, really loud, that's detonation. But if we had a class on diesel engines, I tell you that's normal in diesel engines to have detonation or pinging, but it's definitely not the norm in airplane engines. Typically, aviation gasoline burns at about 100 feet per second. If we had a cylinder with a piston again, and we looked at it from the top, so we looked at it from the top, and we had a spark plug over here, and we had a spark plug over here, and we looked at that fuel as it burned across the cylinder, the spark plug would fire, and the flame would start propagating across the top of the cylinder, and the speed that this fuel would burn, if we measured the speed of this flame propagation across the top of the cylinder, that's 100 feet per second. Now you go 100 feet per second, the speed of sound is 1,100 feet per second. It's only 1/11th the speed of sound. That's true, but you got to realize we don't have to go very far. This distance here might only be 2 or 3 inches for one flame front and 2 or 3 inches for the other flame front. So it's going to take a very, very small length of time to go across it, but it does take time. And as that piston is coming up towards the top of the cylinder, just before it gets to the top, the spark plugs are in there, and the spark plugs fire, and the flame starts propagating. But of course, the piston moves up close to the top, and then this hot gases in here expand and push down. So there's a pressure. There's a high pressure in here, and now that piston starts moving down, and the fuel is still burning. So by the time the fuel gets burnt, that piston is quite a ways down. Let's see if I can do that. So the piston is quite a ways down. By the time the fuel gets finished burning, the piston is quite a way down. I said that enough times, didn't I? So this flame, we have quite a large volume in here by the time all of the fuel gets burned. So a certain amount of energy is going to cause a certain amount of pressure, but the pressure tends to go down if the volume gets bigger. So the pressure in here never gets too high because we're pushing the piston down and the piston's moving and the volume goes up. Now, what's bad is that if we have detonation, this fuel doesn't burn smoothly. We don't have this nice, Try again. If we have an instantaneous burn or detonation, instead of this fuel burning really nice, whoops, instead of this fuel burning nice across here, it all burns at once. So when the piston is up near the top, and we have a small volume in here, but all of it catches on fire at once, then the pressure goes way, way up because the volume is a lot smaller than it would have been. Usually the piston has gone all the way down by the time the fuel gets burned. All of it gets burned. But if we burn all of the fuel and the volume is small, then the pressure is going to go out the roof. So we're going to have a really, really, really high pressure. In fact, if we were measuring the pressure, if we had time and we were measuring the pressure, and we had a nice little graph here, then we'd be cruising along and we'd have a pressure spike. What we'd really like to have is something nice and smooth. And this pressure spike is what's bad, because this high pressure here, this really, really high pressure, is acting on the walls of the cylinder. It's acting on the side walls, and it's acting on the top, and it's acting on the top of the piston. And just like other airplane parts, they were only designed to have a certain amount of pressure and maybe 10% more. So if we have 10% higher, but the capability of the metal to handle it, but the pressure goes way, way beyond that, then we're overstressing the engine. We're doing things to the engine that it was not designed to do. Doesn't want to let me. Oh, I see. Doesn't want to let me do that. In any case, so this overpressurization can hurt the structure of the engine. And this detonation is typically caused by one or three, or I guess it could be more than one at the same time, factors. Either you put in too low of an octane, and so you get pinging or knocking or detonation. You got to understand, the higher the octane, the slower the fuel burns. And that's what we want. We want the fuel to burn reasonably slow. If it burns too fast, we could have detonation. So too low of an octane means the fuel will burn too fast. High manifold pressure, MAP stands for manifold absolute pressure. The higher the pressure we try to burn the fuel at, the more likely it's all going to catch on fire. And then, of course, preignition is where the gasoline air mixture catches on fire before it's supposed to. That is, before the igniter fires. Hey, speaking of preignition, and there it is. It's whenever you have the fuel air mixture catch on fire before the spark plug catches it on fire. And so what's going to happen is, in this cylinder, let's say that, here we got a spark plug, and let's say that typically when the piston is, I'm just making these numbers up, a half of an inch before the top of the engine, the cylinder, that's when the spark fires and we start getting this propagation. Well, if instead of the piston being a half of an inch away, the piston fires, or the cylinder fires now, and let's just say that it's because this valve right here, the edges are really, really thin and it's really hot, or we have carbon deposits on top of the piston and they're glowing red hot. Ooh, I could do it in red. Yeah, here we go. And the carbon deposits are glowing red hot. Now the fuel starts catching on fire and the pressure in here starts rising, but we still need the piston to move up higher. So this pressure is actually pushing against the piston compared to the direction that we want it to go. So this is going to cause the engine to run rough. We're not going to have as much power because the fuel is actually going to be burning and causing pressure in the wrong against the piston at the wrong time and trying to push it down when we want the piston to come up. And you can get this preignition by having spark plugs that got overheated, exhaust valves that got overheated, or carbon deposits somewhere either on top of the piston or on the top of the cylinder. And these are things that you can't do anything about, which is why you have airplanes inspected. They're definitely going to take a look inside the cylinder and see what it looks like on an inspection. Octane. I already told you that higher octanes mean the fuel burns slower, which means you have less knock, less pinging, less detonation. And technically, octane goes up to 100, and after that is performance numbers, but everybody calls it octane. Of course, you've all heard of the 8087. If you lean it, it's got the anti-knock capability of 80. If it's rich, it's 87. They actually took some gasoline. It's made out of a lot of different hydrocarbons, and they refined it until they had just a pure certain hydrocarbon called octane. Octane is one of the hydrocarbon molecules that's found in gasoline, and they refined it so it was 100% pure octane. And when you ran it 100% pure octane and you tweaked it till you got no pinging at all, and then tweaked an engine until you got no pinging at all, no knocking at all, they said, okay, this is 100. So if they messed with it, the engine, and caused too high of a compression, or put in lower octane in the same engine, then the engine would ping or knock. So that's where the numbers came from, was burning pure 100% octane molecules, and that was equaled 100. Of course, everybody knows who's flying little airplanes, 100, 130 is green, and it's got 4 cubic centimeters or 4 milliliters of tetraethyl lead in it. 100 octane low lead, or 100 LL, it's got blue dye in it. It's got 2 milliliters or 2 cubic centimeters, 2 cc's of tetraethyl lead per gallon. That's half of what it used to be, of what 100 octane was. But the problem with lead is the combustion products, if you have lead in your gasoline, pollute the planet. And the EPA, back when they told cars you had to go to unleaded, they let airplanes get away with it because they said, oh no, we need the lead, otherwise it'll be bad for engines. And then 115, 145, that's the good stuff. That's purple. It's dyed purple. Of course, all of these are dyes they put in it, so pilots can recognize what kind of fuel is in their airplane. And if you look at high-performance engines, we're talking World War II, Korean War era, high compression engines where the manifold pressure, because of a turbocharger or supercharger, would get up to 40 or 50 inches of mercury, then you'd need a lot more than even 100 octane. Of course, we don't like things to get in our fuel that cause our carburetors or fuel injection systems to get clogged up. That's why we drain the bottom of the fuel tank to get any sediment or get any water out of it. One of the reasons why you tend to try to fill up fuel tanks in advance, or correction, you fill up your fuel tanks after you land, is because, let's say you burn half of the fuel out. So half of the top of the fuel tank has water vapor in it. So if here's your fuel tank, and the fuel is halfway up there, what's going to happen is that at night, the air inside of here, this air also has water vapor. Of course, around here we don't have a lot of water vapor, but let's talk Daytona Beach, Florida. And it's a nice warm day, and it's 90 degrees Fahrenheit. And the sun goes down, and it cools down, say, to 60 degrees Fahrenheit. Well, inside of here, the H2O, the water inside the air, the water vapor in the air, if we go from 90 down to 60 degrees Fahrenheit, some of this water vapor is going to condense, and it tends to condense along the sides of the tank, and it'll condense on top of the fuel as well. And so what tends to happen now is, with a little sloshing, it'll wash the water off and it'll get down into the fuel. Or if we just fill it up with fuel, all that liquid water is still in there. Now, fortunately for us, gasoline is less dense than water. That is, water is more dense or weighs more. So what tends to happen is the water tends to go to the bottom of the tank. And if we're smart, then we built a tank that goes slightly down a little bit, and we've got a sump drain right here, then all the water goes to the bottom. And hopefully any sediment does too, and we can drain it out. Yay, that works out pretty good. So to try to reduce how much water gets in there, you could tend to try to fill the tank up after you're done flying, if you know that it's a humid day and it's going to get cooler during the night. Selector valves. You're used to using manual selector valves in the Seminole or the 172, but when you get into bigger airplanes, these valves, you don't want to have to use the weight to run a fuel line all the way up to the cockpit to a selector valve and then all the way back. And besides, these fuel lines are going to be a lot bigger than 1/2 of an inch in diameter. We're going to be talking 1, 2, 3, 4, 5, 6 inches in diameter for big ol' honkin' jets. So we're going to leave those selector valves out in the fuel system next to the engine, and we're going to have electrically powered ones. We're going to flip a switch in the cockpit, and it's going to activate a solenoid to move that valve for us. Of course, we need fuel pumps. You're pretty much always, if there is a fuel pump, you're going to have an engine-driven pump. It's bolted to the engine. There's no way to turn it off. If the engine is running, then the engine-driven pump is running. And on many, many engines, that's enough. Even if the electric pump doesn't work, the engine-driven pump will suck the fuel. Even if the fuel is a little lower than that carburetor is, it'll get the fuel out of it. Like if you fly a Seminole, I bet you that you turn on the electric boost pumps. Of course, the engine-driven ones are always running, but you turn on the electric boost pumps for takeoff and landing and maybe climb. But at cruise, at least I flew a low-wing Cherokee. At cruise, after you leveled off, you would turn off the boost pump because you didn't need it anymore, and you just used it then. In addition to takeoffs and landings and maybe climb, you would only use it if the engine-driven pump failed. Of course, filters can't always drain out all the sediment, so you want to make sure you don't clog up your carburetor or your fuel injection system. And of course, we've got to have fuel lines to get stuff from the fuel from the tank to the carburetor or fuel injection system. And then, of course, you have to store all this fuel, which fuel is your friend. It's to store lots of fuel in fuel tanks. Speaking of fuel tanks, there's typically 3 kinds. The ones we have out at the flight line, we've got our nice low-speed airfoil, and inside that, and of course this isn't a great picture, but inside that we have a metal tank. And this metal tank is bolted down to the metal of the wing. And so the structure, and of course we've probably got a spar right here, and we probably got a spar right there. So the wing structure is completely separate than that of the fuel tank. And that works out okay. It does weigh a little more than it could, but it's very easy, and the fuel tank is separate, so if it leaks, you have to drill out rivets on the skin here, but you can take the tank out. And so that's the bolted-in kind. That's what we typically have on light airplanes. Now, a bladder tank, let's see if I can draw a bladder tank. A bladder tank, instead of using metal, is made out of rubber. And this rubber is tied down, and it works out pretty good because you don't have to worry about the corners of the metal having sealant and and starting to leak. And the nice thing is, you can also, if you have a let's see if I can do this. All right, you can make the bladder fit. Let's say you have your spars right there. You can make the bladder tank fit exactly the same size as the inside opening, and so you're using up all the volume. Of course, the downside to bladder is it's rubber, and after 10 years it's probably going to deteriorate. Maybe 20, you'll have to replace it. Then there's the integral type, and if you look on transport category jets, big biz jets, big turboprops, you're going to see the integral kind. The integral kind is, say, here's a spar and here's a spar, and they put sealant in all the corners. And literally now, the tank is the fuel. Or correction, the wing is the fuel tank. That is, the skin of the wing is also the tank. So that's the tank, as well as the skin of the airplane, and this saves weight, which of course is a big deal, especially if your fuel tanks have to hold tens of thousands or hundreds of thousands. I mean, let's face it, if you're in a 747-400 and your max gross takeoff weight is 800 or 900,000 pounds, 200,000 or 300,000 of that could be fuel. That's just a lot of fuel. So if we had to have the weight of this bladder, or we had to have the weight of this extra metal, that would cause the empty weight to be higher. excuse me, and we'd have to carry less payload, less passengers, less fuel. So if you look at transport category jets, big biz jets, big turboprops, they're going to have to seal all these rivet holes, and they're going to have to seal all the corners. So that becomes the issue. That's the downside, is leaks where the sealant goes bad. But it's worth it because you save so much weight. And of course, sump drains. If you've drained a sump out of an airplane, then you know what I'm talking about. And vents. If we pump fuel out, we're going to have to let some air in. So that's why it's typical on light airplanes. Part of the pre-flight is to find the vent and make sure it's not clogged up by a wasp's nest or anything like that. Stick in the tank. Let's see. Well, here, let me go back one. Let's just say that you're doing your 172 pre-flight, and there's a tank in here. And you put a straw down in here, and you put your thumb over it, and then you lift it up. And so now you look at this straw with your thumb over it, and the fuel's right there. You could calibrate this straw. If the fuel was right there, you'd know how much fuel there was. So you could put notches or marks on this straw, and this is one way to stick the tank. Back when I learned to fly, back in the 1940s, we just took a piece of wood and stuck in there and pulled it back up. We had a piece of wood, and you could see that it was wet up to a certain point, and it was calibrated. Of course, the downside to that is if you throw this piece of wood in the back of the airplane, now you have a flammable piece of wood, and it stinks. But other than that, it worked out fine. Oh, yeah, and then, of course, pieces of wood could fall off. So a nice clear straw works pretty good, and you can buy these for certain light airplanes. Now, that's stick in the tank. You're essentially putting a stick in the tank. However, on transport category jets, the wing is pretty high up, and there's multiple tanks. It's a big pain in the butt. So what you're going to do here is, let's say here's the fuel tank. Here's the bottom of the wing. Whoops. Here's the bottom of the wing. And here's the top of the wing. And here's the level of the fuel. There is a float with magnets in it right here. And then there's a tube. Here, you can see this tube. And inside this tube has some more magnets, and it's got this calibrated markings on it. And you pull this tube out, and there's O-rings in there, so the fuel can't get out. And you pull it down, and when the magnets on the inside hit the magnets on the outside, they grab each other, and now this tube doesn't want to come down. This stick doesn't want to come down any farther. You notice here's 7, 8, 6, 5, there's 4. So this could be like 7,000 pounds of fuel. So right here, here's 5, 475, 450. So it's about 4,500 pounds is what is showing right there. So that means that's what's left in there. Now, you got to understand that this is really measuring volume. It's measuring this height here, which relates to volume. But if the fuel is hot, it will have expanded. If it's cold, it will have contracted. So what you're going to probably have to do, and here's a picture of what it would look like under the wing. You pull this part down here. What you're going to have to do is take this reading and enter a chart and correct it for temperature. That is not the outside air temperature, but the temperature of the fuel. It's going to have to be corrected onto that reading, because if the fuel is hot, it will have expanded, and if the fuel is cold, it will have contracted. If you have any questions about fuel systems, please don't hesitate to get a hold of me. Thank you very much.